Since 2017, a nearly 50-year-old spacecraft more than 15 billion miles from Earth has been quietly recording something that shouldn't be there. Not a burst, not a one-time event. A faint, steady, continuous hum buried in the data that has never gone away, that nobody was specifically looking for, and that, even now, years after it was first noticed, scientists still cannot fully agree on the cause of. It isn't loud. It isn't dramatic. If you turned the raw data into sound, most people would barely notice it at all. But its very existence has puzzled the small group of physicists who study it closely, because everything about how this kind of signal is supposed to behave says it shouldn't be this consistent, this stable, or this persistent for this long in a region of space this empty. This is Voyager 1's plasma wave instrument, one of only 2 working instruments left on the entire spacecraft, still listening from a place no other human-made object has ever reached. And what it picked up, starting in 2017, is one of the strangest, quietly unresolved mysteries in modern space science. Not because someone made it up for a headline, but because 2 published, peer-reviewed research teams have proposed 2 different physical explanations, and neither one has been able to fully rule out the other. By the end of this video, you'll understand exactly what this signal is, why it matters, and why, even with everything we've learned from Voyager 1 over nearly 50 years, this is one question the spacecraft still hasn't answered for us. To understand why this signal is such a big deal, you first need to understand exactly what's doing the listening and how much that machine has already been through. Voyager 1 launched on September 5th, 1977, built to survive a 5-year mission past Jupiter and Saturn. It has now been operating for nearly 49 years, almost 10 times longer than anyone originally designed it to last. In August 2012, it became the first human-made object in history to cross the heliopause, the boundary where the constant outward push of our sun's solar wind finally gives way to the pressure of true interstellar space. Voyager 1 didn't just visit that boundary, it kept going, and it's been sending back data from beyond it ever since. The only spacecraft in existence with a direct, uninterrupted real-time connection to the space between the stars. But keeping that connection alive has meant sacrifice after sacrifice. Voyager 1 runs on a radioisotope thermoelectric generator that converts the heat from decaying plutonium into electricity, and that power source loses about 4 watts every single year, with no way to ever refuel it. As of April 2026, it's producing less than half the power it had at launch. To survive on a shrinking power budget, NASA has had to permanently shut down instrument after instrument over the decades, the imaging system and ultraviolet spectrometer back in 1990, the cosmic ray subsystem in February 2025, and most recently, on April 17, 2026, the low-energy charged particles instrument, which had been running almost continuously since 1977. That leaves exactly 2 working science instruments on the entire spacecraft: a magnetometer that measures magnetic fields, and the plasma wave subsystem, the instrument this video is actually about. As NASA's own mission team put it when they announced the most recent shutdown, these last 2 instruments are still working great, still sending back data from a region of space nothing else has ever explored. The plasma wave subsystem doesn't work like a camera or a simple sensor. It essentially acts as a radio receiver, tuned to detect oscillations in the thin, charged particle soup that makes up interstellar plasma, the extremely sparse material that exists in the space between star systems. For decades, the way scientists used this instrument to measure the density of that plasma was almost accidental. They waited for shock waves, triggered by solar eruptions on our own sun millions of miles away, to ripple all the way out past the heliopause and rattle the plasma near Voyager 1, producing brief, detectable oscillation events. Between those rare shockwave events, there was mostly just silence, no reliable way to measure the plasma density in real time. This instrument has already proven itself once before in a moment that made history. Back in 2012, it was actually the plasma wave subsystem's detection of a sudden, sustained jump in plasma density, not the more commonly cited magnetic field data, that gave scientists their strongest evidence that Voyager 1 had genuinely crossed into interstellar space. Even so, NASA didn't officially confirm the crossing right away. For over a year, it remained an open scientific question, first identified in March 2013 based on the August 2012 detection, but not confirmed by NASA until September 2013, after independent teams cross-checked the plasma data against other measurements to make sure the interpretation held up. That cautious, months-long confirmation process says something important about how this kind of science actually works. Even a clear signal takes real-time and independent scrutiny before scientists are willing to call it settled. Then, starting in 2017, something changed. In data collected from 2017 onward, a research team led by Cornell astronomer Stella Koch-Ocker found something the plasma wave subsystem had never reliably detected before: a very weak, narrowband emission sitting almost exactly at the local plasma frequency, essentially a faint, continuous tone, rather than the brief bursts scientists were used to seeing. And unlike the shockwave-triggered events, this signal wasn't a one-time spike. It just kept going, persistently, continuously, for years. That persistence turned out to be genuinely useful, scientifically. Because this faint signal never disappeared, it gave researchers something they'd never had before: a steady, continuously sampled measurement of interstellar plasma density gathered across roughly 10 astronomical units of space, with individual readings spaced only about zeros. We were 3 astronomical units apart. An extraordinarily fine-grained continuous dataset, instead of scattered rare snapshots separated by huge gaps whenever a solar shockwave happened to pass by. Using this new method, the team was able to map small-scale density fluctuations, tracing actual turbulence in the interstellar medium, filling in the picture between the widely spaced shockwave events that had given scientists their only previous data points, going back to Voyager 1's very first interstellar plasma detections published in Science back in 2013. So here's the actual scale of what this spacecraft has quietly been doing. From a distance of more than 15 billion miles, using an instrument originally built in the 1970s, with a power source now producing less than half its original output, Voyager 1 has been continuously mapping the fine structure of interstellar plasma turbulence in a way nothing else humanity has ever built could replicate. Not because NASA planned it that way from the start, but because engineers and scientists noticed something faint and strange in the data and figured out how to turn it into a genuinely new scientific tool. It's worth pausing on just how difficult this measurement actually is. Voyager 1 is currently more than 25 billion kilometers from Earth, about 7 billion miles. A radio signal traveling at the speed of light takes roughly 23 hours just to reach it, and another 23 hours for any response to come back, meaning every single data point in this dataset represents information that took the better part of 2 full days to travel from the edge of the solar system to a listening station here on Earth. And the plasma being measured is almost unimaginably thin. The interstellar medium out there contains only a fraction of a particle per cubic centimeter, compared to the vastly denser plasma inside our solar system's heliosphere. Detecting a faint radio hum at that density from that distance, using 40-year-old electronics and turning it into a usable scientific measurement, is itself a genuinely remarkable technical feat. One that nobody who built Voyager 1 in the 1970s could have specifically planned for, because the entire concept of measuring interstellar plasma turbulence this way didn't exist yet. And yet, the question of exactly what's producing that faint, persistent tone in the first place, the very thing that made all of this possible, still doesn't have a fully settled answer. Here's where this stops being a simple spacecraft finds something cool story and becomes a genuine, ongoing scientific disagreement. When the Ocker team first published their findings, they proposed 2 possible physical explanations for the persistent narrowband emission, and were careful to say the true cause could be clarified by new findings. In other words, they didn't claim to have solved it. The first possibility is that the signal comes from thermally excited plasma oscillations, essentially electrons in the interstellar plasma jiggling around due to their own heat energy, naturally producing a faint radio signal at the local plasma frequency, simply because that's what warm, charged particles do in a very sparse medium like this. The second possibility, explored in more detail by a separate team publishing in the journal Astronomy and Astrophysics, is something called quasi-thermal noise, or QTN, a subtly different physical mechanism first identified in our own solar system's solar wind back in 1979, where the collective, near-random thermal motion of electrons around the spacecraft's own antenna produces a characteristic voltage signature that peaks right at the local plasma frequency. QTN has been reliably observed before by plasma instruments on missions like Cassini and Galileo, so it's a well-understood phenomenon in principle. The open question is whether Voyager 1's specific antenna, which is far shorter than what's typically used for this kind of measurement, and far outside the environment it was originally tested in, is actually capable of producing a clean QTN signature this far from the Sun in this specific plasma environment, or whether something else entirely is going on. Neither team has been able to fully close the case. The researchers who first identified the signal explicitly noted that thermally excited plasma oscillations and quasi-thermal noise are both plausible mechanisms, and that distinguishing between them, or ruling out some third possibility entirely, would require either new analysis of Voyager's own data or measurements from a future dedicated interstellar mission carrying instruments purpose-built for this exact kind of detection. Voyager 1 wasn't designed with this specific question in mind. It's a nearly 50-year-old antenna, originally built for entirely different measurements, that happened to be sensitive enough to catch something nobody fully anticipated in an environment nobody had ever directly sampled before 2012. The quasi-thermal noise explanation is particularly interesting because of how well established the underlying physics is everywhere else. QTN was first identified in our own solar wind back in 1979 by physicist Nicole Meyer-Vernay. using a radio receiver aboard the ISE-3 spacecraft, at the time, the most sensitive instrument of its kind ever flown. Since then, it's been detected reliably by plasma instruments on missions exploring Saturn, Jupiter, and other parts of our own solar system. So scientists have decades of solid comparison data for what a clean QTN signature normally looks like. The complication with Voyager 1 is that its plasma wave subsystem uses a notably short antenna compared to the kind of instrument QTN research usually relies on. And general plasma theory suggests that antennas shorter than a certain physical scale, related to something called the Debye length, which describes how far electric fields can extend through a plasma before being shielded out, can struggle to produce a clean, unambiguous QTN signature. Whether Voyager 1's specific antenna on this specific spacecraft in this specific ultra-thin interstellar plasma clears that bar or not is exactly the kind of technical detail that keeps this question genuinely open rather than settled. That's what makes this a genuinely open scientific question rather than manufactured mystery. There's no vague, unnamed scientists or baffled claim here. There are two specific named research teams publishing specific competing physical models in peer-reviewed journals, actively trying to figure out which explanation fits the data better, using a signal that has now persisted, essentially without interruption, for close to a decade. And there's an added layer of urgency to actually solving it. According to long-term planning documents for future interstellar missions, Voyager 1's power reserves are expected to run out entirely by around 2036, at which point this specific antenna on this specific spacecraft in this specific irreplaceable location in space will simply go silent forever. Whatever we haven't figured out about this signal by then, using Voyager 1's own data, may not get a second data set to work with for decades. No other spacecraft is currently positioned to take over this exact measurement the moment Voyager 1 goes quiet. It's worth stepping back and asking why a faint, practically inaudible radio hum picked up by a decades-old antenna is worth caring about at all. Because whichever explanation turns out to be correct, it fills in a piece of physics we genuinely don't have anywhere else. If it's thermally excited plasma oscillations, that tells scientists something specific and useful about the temperature and density conditions of the true interstellar medium, the actual physical environment that exists between star systems, which almost nothing built by humans has ever directly sampled. If it's quasi-thermal noise instead, that tells scientists something important about how spacecraft instruments themselves behave at extreme distances, which matters enormously for designing the next generation of interstellar probes correctly, so they don't run into the same ambiguity Voyager 1's much older antenna created. Either way, the answer helps refine models of the interstellar medium that current and future missions rely on. NASA's own long-term planning documents for interstellar exploration missions explicitly flag Voyager 1 and 2 as an irreplaceable singular dataset, noting that no other spacecraft currently has an instrument suite capable of directly measuring this specific slice of near heliopause space, and that once Voyager's power runs out around 2036, that gap in direct measurement will remain until a dedicated future interstellar mission is designed, built, and flown, which realistically could take decades. So this isn't a minor academic curiosity. It's one of the only continuously running physics experiments humanity has ever operated in true interstellar space, using hardware that was never specifically built for the job, that happened to be sensitive enough to catch something nobody expected, and that we are actively racing against a hard power loss deadline to fully understand. There's also a broader reason this particular puzzle matters beyond Voyager 1 itself. Every future mission concept aimed at interstellar space, and there are several currently being studied by NASA and other space agencies intended to eventually follow in Voyager's path with modern instruments, has to be designed using our current best understanding of what the interstellar medium actually looks like physically. If the persistent signal turns out to be thermally excited plasma oscillations, that tells mission designers something concrete about the natural temperature and density conditions their future spacecraft will actually fly through. If it turns out to be quasi-thermal noise instead, that's an equally important lesson, but about instrument design. A reminder that even a well-built antenna can produce ambiguous readings if it's shorter than the physics of the local plasma requires, which is exactly the kind of design flaw future engineers would want to avoid repeating on a mission that might not get a second chance either. So here's where this actually stands right now. Since 2017, Voyager 1 has been continuously picking up a faint, persistent radio signal from interstellar space that has never gone away. Two separate teams of researchers have proposed two different physical explanations for it: thermally excited plasma oscillations, or quasi-thermal noise from the spacecraft's own aging antenna, and neither has been fully confirmed or fully ruled out. The signal itself has become genuinely useful, giving scientists their first continuous, fine-grained map of turbulence in the true interstellar medium. But the fundamental question of exactly what's producing it, physically, at the most basic level, is still open. And Voyager 1 doesn't have unlimited time to help us figure it out. Its power keeps dropping every year. Engineers keep having to shut down more of it just to keep the lights on. Current projections suggest it could run out of usable power entirely by around 2036. And when that happens, this specific measurement from this specific irreplaceable vantage point stops, with no other spacecraft currently positioned to pick up where it left off. So the real question isn't whether Voyager 1 has anything left to teach us about the space between the stars. It clearly does. It's been quietly doing exactly that, in a form nobody fully expected, for almost a decade now. The real question is whether we manage to fully understand what we're actually looking at before this nearly 50-year-old machine finally runs out of power for good. If you want to be here when new research finally settles which explanation is correct, or if it stays unresolved right up until Voyager 1 goes silent, subscribe to the channel and turn on notifications. Because the moment new findings come out, we'll break them down here with the real data, not the invented version. One faint signal, 9 years and counting, still not fully explained. Thanks for watching.